Okay, everyone, it's time for us to get started. This is our third day for the analysis class, and I hope that a few more people show up. Where we left off last time was that we had written down the algebraic properties for real numbers, and we were starting on our first theorem that had three parts, and we had done one part. So let me write down the theorem, and we'll prove the other parts today. As the theorem, what we had is, if Z and A are real numbers, so elements of the real number, with Z plus A being equal to 0, then Z had to be equal to 0. That's something we showed. Part B, if U and B are elements of R, with B being different than 0, and I'll say that, or it says that U times B is equal to 1, or equal to B, then U had to be equal to 1. Part C says, if A is a real number, then A times 0 equals to 0. Okay. So we want to prove these items. Let me go back so I can write them down. And we'd already proven part A. So I'm starting to do this. This was done last time. So here's the proof for part B.
For part B, I think I can do it directly.
We will let U and B be real numbers, with B being different than 0, and we're also going to have the quality that U times B equals to B. We want to show U equals to 1. I'm not sure that I will be doing this exactly the same that the book does, but maybe I am, because the book has it proved as well. Okay, so we're letting these things happen. I want to show that U equals to 1. Well, note, let's start off with U. U is equal to U times 1. So there's this number, real number 1. We learned from the algebraic properties of the real numbers. There's this number 1 that when you multiply any number by 1, you just get that number. So U times 1 is U. Okay? Now I'm going to rewrite 1 as U times B times 1 over B. Now, I know B times 1 over B is 1, because B is a non-zero number, non-zero real number, so I know 1 over B exists, multiplicative inverse, such that if you multiply by B, you get 1. Now, through the associativity property for multiplication, I can rewrite this as U times B first, then times 1 over B. And the reason I want to do that is because I have a fact, in terms of what I'm assuming, about U times B. So for here, and this should be equal, okay? U times the quantity B times 1 over B is the same thing as U times B, that quantity times 1 over B. That's why I should put equals. This U times B is equal to what? What are we assuming it's equal to? B. So we have B times 1 over B. But what's B times 1 over B? Very simple thing. What's B times 1 over B? That's 1. Look at this string of equalities. It starts with U and it ends with 1. So in this situation, U had to be 1. That ends that proof. Okay, part B. So now we want to do part C. For part C, to prove it, remember we're working on this statement we had ended with last time. I just did part B of the statement. For part C, we want to show, or we're going to let A be a real number. we want to show that A times 0 equals to 0. Now this is kind of indicative, just a little bit, of what we're doing in this class. We're making sure that we're having logical arguments, proofs of facts that maybe we already know. Listen, a number times 0, what is that? 0. Okay? We're just making sure we can prove it. Now, I'm going to, on the side, I know it's off camera, but I'm going to, on the side, write down part A of this theorem. It said, if z plus A equal to A, then z had to be 0. That's something we've already proven, okay? So I'm going to keep that in mind because I'm going to use it for part C here. I want to show that A times 0 equals 0. Well, note that A times 0 is the same thing as A times, instead of 0, I'm going to write down 0 as 0 plus 0. Because if I add 0 to anything, I just get the anything. And so if I add 0 to anything, I just get the anything. Now I can use the distributive property, and that will be equal to A times 0 plus A times 0. So that's a string of equalities. So the first thing I've written is equal to the last thing that I've written. Thus, I'll rewrite this in this form. A times 0, the last thing that I've written, plus A times 0, so the last thing that I've written, is equal to A times 0. I'm going to move the camera so we see this.
I've written on the side board here.
The part A for this theorem. The way that we can think of part A in this theorem, it says if z plus A equals A, then z had to be 0. Here's a way of understanding this statement. If you got a first thing plus a second thing equal to the second thing, that means the first thing had to be 0. I'm going to say it again. This is a way of understanding this theorem. If you have this part of it, if you have a first thing plus the second thing equal to the second thing, the first thing had to be 0. Look what I've got right here in the proof of part C. I've got a first thing plus a second thing equal to the second thing. So what does that say? It says the first thing had to be, and I want to show A times 0 was 0. So that's the way of doing it. All right, so that concludes that proof. We'll give everybody a second to write this down. Okay, I'm going to erase this right-hand side. The next thing I'm going to do is look at another statement from the book, I believe. So here's the theorem. It's got two parts. It says, for part A, it says, if A is different from 0 and B is an element of R, are such that A times B equals to 1, then B equals to 1 over A. The second part of the statement is if A times B equals to 0, then either A equals to 0 or B equals to 0. And we won't prove this in parts. Okay. So I can prove part A directly, I believe. I'm going to let A and B be real numbers with A being different than 0, and A times B equaling 1. What I want to show is that B had to be the multiplicative inverse of A. That's what I want to show. B has to equal 1 over A. That's what my job is. Well, since I want to say something about B, let me grab B. Let's note, I'm going to start with B. And I'm going to note that B is equal to B times 1, because 1 times anything is the anything. And now, as I've done before, I'm going to rewrite 1 in a special way that involves A, because I know something about A and B being multiplied together. So I can rewrite 1 as A times 1 over A. And I can do that because A is, I can't do that for every number. I can do it for almost every number. But there's one number, 0, which I can't write down as multiplicative inverse because it doesn't have one. But I know A is not 0. So that's what we have to do. So this can be rewritten as B times A, that first, and then times 1 over A. And being very cautious here and running through every step, I can rewrite B times A as A times B, the commutative property of multiplication. And then that's got to be multiplied by 1 over A. But what's A times B by our assumption? We're assuming that A times B is equal to 1. So this part we can substitute 1 in for. So we have 1 times 1 over A. Well, 1 times 1 over A is 1 over A. And so I'll make a conclusionary statement, but what we found is B is equal to 1 over A. And that's what we wanted to show. Let me write that down here. So what we're saying here is that B is equal to 1 over A, and that concludes the first part of this theorem. Now I want to show the second part of this theorem. So here's proof B. The statement for B, okay, it's on the other side of the board. I'm going to read it. The statement says, hey, if A times B equals to 0, then either A was 0 or B is 0. Well, that's a big fact. That's something we use in algebra all the time. When we're trying to solve, often when we're trying to solve equations, algebraic equations, if you can factor one side and it's equal to 0, then one of those factors had to be equal to 0. That's exactly what that's saying. We got a name for it. Does anybody remember what the name of that property is? It's called the zero product property. Something times something equals 0. One of those things involved in multiplication had to be 0. Is that okay? That's what we're being asked to show. Okay, so we'll let A times B equal to 0. We must show A equals to 0 or B equals to 0. That's what they show. Well, by the way that the statement is written, we had a proving technique for such statements. It's one where we say, well, if A equals to 0, it's kind of like cases on the conclusion. If A equals to 0, then the statement is true. When we're done. So that's one case. The other thing that we consider is if A is not 0, then what do we have to show? B is. Yes, we must show B is 0. Okay, so let's take a look at B. So here, I'll notice that B is the same thing as B times 1. And I can rewrite 1 as A times 1 over A. And the reason I can write down 1 as A times 1 over A is I'm assuming, in this instant, that A is non-zero. That's why I can do that. Well, reassociating, I have B times A times 1 over A. Commuting, I have A times B times 1 over A. And then that's equal to 0 times 1 over A. we had just proven in that three-step theorem we listed before, the only theorem we listed before. If you look at the last statement from our first theorem, it says if you have A times 0, you get 0. Anything times 0 is 0. Well, here I've got anything times 0, so I better get 0. So B had to be 0. This is a string of equalities. It says B is 0. Therefore, this statement is true in all possible cases. And that ends this theorem. Okay. The next thing I want to do is that I want to remind you that we have these algebraic properties of R. And the algebraic properties of R were based on two operations that we had on the real numbers. Do you remember what those operations were? Addition and multiplication, that's right. But we know we can do more things between numbers. What else can we do? Yeah, that's right. We can subtract and divide. So here, as a definition, we will define A minus B as A plus minus B, where we consider minus B as the additive inverse of B. Megan, when you first learn, Adam, when you first learn about subtraction, John, when you might have remembered that people told you, really we turn a subtraction into an addition and we change the sign of what follows. That's what we tell younger people when they first start to learn. Well, that's what we tell older people too. That is the definitions. That is it. So it's not something made up. That's what we think of in higher mathematics. Exact same thing. Okay. That's one statement. We will define division A over B, where for B being non-zero, as A over B is the same thing as A times 1 over B, where 1 over B is the multiplicative inverse of B. So that's the way we work. The next thing I want to list is something called the order property on an R. And it establishes the existence of positive numbers. Okay, that's what it does. So that's what I'm going to talk about next. This is out of our book. It's on page 26 of our text, and that's what I'm going to write up on the board next. So it's the order property on R. It says there is a, this is a key, non-empty subset of R, say P, that's what I'm going to do now, strip P, which is the positive numbers which satisfies three things. Here's the first thing. If A and B are positive numbers, then A plus B is a positive number. You take two positives, add them together, you know what you get? You get a positive. Not only will that happen, but if A and B are positive numbers, if you multiply them together, that's multiplication. You multiply them together, that's a positive number. And the third statement involves the set of positive numbers, but it starts off with, for any real number A, for any A element of R, exactly one of the following occurs. So either A is a positive number, or A is 0, or the third thing that could happen is the additive inverse for A, minus A, is a positive number. And that establishes the positive numbers. Those characteristics involving this set and with real numbers is what establishes the positive numbers. From the positive numbers, we can define what it means to be less than. Okay? And that's what I'm going to find next, or less than, or equal to. Here's the definition. I'm going to write it this way. Given two numbers A and B, and I'll say, well, they're real numbers, okay? Then A is less than B if B minus A is a positive number. That's what we're going to find. So what does it mean to be one number to be bigger than another? If you take the smaller from the bigger, you're positive.
So what was the definition? What is this actually defining? Bigger numbers?
Less than.
Okay. Less
A similar definition, given A and B element of R, then A is less than or equal to B if, and let me write down, A is less than or equal to B, that's what I'm saying. If B minus A is an element of the set of positive numbers union 0. So B minus A is either positive or it is 0. That's how we're defining less than or equal to. Anytime that you have any questions, please feel free to ask. No worries. All right. Well, the first thing I want to tell you is I want to write down a fact. It's a very minor fact, but something that can come in handy for thinking positive numbers. So here's a fact. It says A is a positive number if and only if A is greater than 0. So what does it mean to be a positive number? It means you're bigger than 0. This is not something in the book, it's something I'm telling you. I will prove it. And we're going to take our time about this. It's an if and only if statement. That was the last type of statement that we said anything about proving. Let me turn it down here.
So the statement we're talking about is the following.
It's if A is a positive number, then A is a positive number if and only if A is greater than or equal to 0. That's what we're talking about. Okay. So, as I was saying, it's an if and only if statement. You have two directions to show. You've got to show if, and this is the way we'll indicate we're going in this direction. What does this direction mean? It means we're assuming the first part, we've got to show the statement. So let A be a positive number. We must show A is greater than 0. I told you we're going to take our time. No rushes. Here's what I'm thinking. I'm thinking I've got to show A is greater than 0. How can I show that A is greater than 0? Well, how do I show any number is bigger than another number? I've got to show that the bigger minus the smaller is what? Positive. That's what I got to show. That's what it says over there. For one number to be bigger than another, the bigger minus the smaller has got to be element of positive numbers. Is that okay? That is, we must show A minus 0 is an element of positive numbers. That's what that is. All right, well, here's the first thing I want to say. Well, note that 0 plus minus 0, well, this is a number, and then putting a minus in front of it makes it its additive identity. So you take a number and its additive identity, what do you get? 0. Thus, minus 0 plus 0 equals to 0. So I'm going real slow. What am I saying here? I'm saying I can commute this left-hand side. 0 plus minus 0 is the same thing as minus 0 plus 0. Why would I want to do that? I want to do that because of this rule is still on the board here. First plus second equals to second. First plus second equals to second. That means the first had to be 0. So what am I saying in this statement? I'm saying that from this statement and from the first part of our first theorem that we've looked at in this class, I can say that minus 0 equals to 0. Okay. Now remember, my goal is to show A minus 0 is a positive number. So, A minus 0 is the same thing as A plus a minus 0, because I can change the subtraction into addition. I just have to add the additive inverse of what was following. Well, what's minus 0? So it's A plus 0. And what's A plus 0? Nope. A. Okay. No worries. It's A.
0.
So that's A. So A minus 0, which is what I'm interested in, is A. But what do I know about A? I'm assuming that A is a positive number. Since A is a, oops, I wrote down R. Since A is a positive number, and A is the same thing as A minus 0, that means that A minus 0 is a positive number. That's not right. Look, I'm going real slow, but we're making sure everything is verified. So that says that A minus 0 is a positive number, thus A is greater than 0. I've proven half of this statement. Remember, it's if and only if statement. I've proven one half. Here's the other direction, and here's how I tell readers that I'm going in the other direction. I put an arrow going in the other direction. What does that mean in this problem? Well, we assume the second part. So suppose or let A be greater than 0. What do we want to show? We want to show A is a positive number. That's what I want to show. Okay. Well, here's what I know. Since A is greater than 0, so I'm asking here, Melissa, to just remember the definition of what it means for A to be greater than 0. What does it mean? What does it mean for one number to be bigger than another? Bigger number minus the smaller number. So that means A minus 0 has to be a positive. Remember, my goal is to show A is positive. But what's A minus 0? We really showed the work on the left-hand side of the board in the midst of this theorem. It's what?
A plus 0.
It's the same thing as A plus 0, which is still A. So A is a positive number. So what we're saying, Megan, is that A is a positive number if and only if A is greater than 0. Is that okay with everybody? John, it's all right? Chuck? All right. Well, that's a fact. That wasn't something that was covered in the book, but it's something I wanted to list for us. Here is a theorem that's got 3 parts to it, and I'd like to look at proving it. It says, let A, B, and C be real numbers. Then we got 3 parts. Really, it's 4 parts. It says, if A is greater than B, and B is greater than C, then A is greater than C. The second part says, if A is greater than B, then A plus C will be greater than B plus C. And the third part C has 2 parts. The first part says, if A is greater than B and C is greater than 0, then C times A will be greater than C times B. Man, let me give everybody a second before I write down part 2 here. Give everybody just a second. What is this part 1 of C saying? It's saying if you have that A is bigger than B and C is a positive number, because if C is bigger than 0, it's positive, and you multiply both sides of this inequality by that positive number, it retains the inequality. We already know that. You multiply an inequality by a positive number, it doesn't change the direction of the inequality. That's all that's being said for part 1, see? And you know what part 2 is? It's the natural other fact that we know. What if you multiply both sides of an inequality by a negative number? That's right. So here, if A is greater than B and C is less than 0, then that means that AC, or I guess I'll write down, CA is going to be less than CB. Those are the things we want to prove. You multiply by a negative, you have to switch the direction of the inequality. All right, so this theorem had 3 parts, and the last part had 2 parts to it. So let's go ahead and start with the proof for part A. Well, for all of them, I'm going to say let A, B, and C be real numbers. Real numbers. Okay? Real numbers. Now, for part A, here's what we're going to do. We're going to let A be bigger than B, and B be bigger than C. What is, part A is still on the board for you to see. What is it that we want to show? We want to show what? Okay. Adam, I want to show A is greater than C. I got one way of showing A is greater than C. It's the definition. What do I have to show for A to be bigger than C? What do I have to do to show that C is less than A?
You gotta show that B is greater than C.
Just involving A and C. One statement. Take your time. What's the definition for C to be less than A? Take your time.
Oh, it's gotta be A minus C, a positive number.
That's exactly what I got to show. Everybody hear that? That's what this means. Chuck, I got to show that A minus C is positive. Adam, that's fantastic. Good. Okay. Well, note. So I keep it in the back of my mind. I want to show that A minus C is a positive number. That's what I want to show. Okay. So, Brad, maybe not know, but since A is greater than B, then using that definition, what's that say? That says that A minus B is what kind of number?
Greater than 0.
That's true, but I'm going to say it's positive. But what you said is right. And can't I say something similarly about involving B and C? Because I have B is greater than C. So what can I say here, Megan? I can say since B is greater than C, what can you say? What's the definition? B is greater than C. That means that B minus C is a positive number. Is that okay with everybody? So look, I've got two statements here. A minus B is positive, and B minus C is positive. Is that okay?
So I think I see where we're going to.
Okay, what do you think, John?
So if you have two positive numbers, you add them together, it's also positive.
That's exactly what I'm going to write next. And that's exactly right.
Thus, and I'm going to even say why. You don't have to. But why is it that we know if you add two positive numbers, you get a positive? Look, I know everybody tells us that. It makes sense. But what has been said in this class that tells us if you add two positive numbers together, you get a positive?
Order property.
The order property of R. That was one of the three things it said, Chuck. What were the three things it says? If you take two positive numbers and add them together, you get a positive. If you take two positive numbers and multiply them together, what do you get? Positive. And if you're a real number, you fit into exactly one of these three categories. Is that okay? All right. So anyway, in particular, thus by the order property on R, A minus B plus B minus C is an element of the positive numbers. Okay. What I'm going to say is that we can rearrange these to be, I'm going to do it. Okay? I am going to do it. What you can do is you can think of this as one thing plus two things here. That's what you can do. And so what I'm going to say is the first, I'm saying take the first thing plus these two things combined. I'm going to rewrite that as this first thing plus this guy minus C. Okay? That's what I'm doing. Then this yields, that's positive. They're the same. These two lines are the exact same numbers. So here this says that A plus C, or just A minus C, is positive. And if A minus C is positive, that means A is greater. And that's what we wanted to show for part A. I'm done with part A. What was part B? So part B, we're going to let A be greater than B. We want to show, no matter what C is, that A plus C is greater than B plus C. That's what we want to show. how am I gonna show that A plus C is greater than B plus C? Well, I'm gonna show that A plus B minus the quantity B plus C is a positive number. That's what I'm gonna show. Well, since A is greater than B, then I know that A minus B is positive. I'm being very careful here. Eventually we're not going to have to be that careful as I'm doing this. I'm just kind of getting us used to proving things. And we're doing things very formal. Eventually we're going to be very accustomed to this, that we'll skip some few steps. Yeah, that's true. Exactly. So here, what I would say is, so A plus 0 minus B is a positive number. That's what I got. Because A is the same thing as A plus 0. That's all I'm doing. So that says that A plus, instead of 0, let me write that down as C minus C minus B. The element of positive number.
And we can reorder them.
Yeah, so I'm going to say, I can rewrite this as A plus C. Do that. Minus C. Or I'll write this down as plus or minus C. And then here I'll write down plus or minus B is an element of positive numbers. And then I'll reorder them again. I'll say this is the same thing as A plus C is one quantity. Plus, I'll write down this quantity, minus C plus or minus B is a positive number. Now, I haven't shown this, but minus C and minus B are really minus 1 times each one of those. And I can factor out a minus 1. Those are two steps that I'm saying I'm doing, but I haven't really shown that you can do that. So I am skipping something here. So A plus C really is going to be minus here C plus B. That's going to be positive. What does that tell me? That tells me that if you want to rewrite it one time, A plus C minus, I'll rewrite this as B plus C is positive. So that it matches perfectly with what we're trying to say. So that right there says that A plus C is greater than B plus C. And that's what we were trying to show. But I am skipping some steps here. There's some things that I'm saying is true, but maybe I hadn't verified. As a matter of fact, I'm going to get you to verify them in homework. Okay? So there are homework problems that this is really based on. One of them is minus C is the same thing as minus 1 times C. Okay? And that would be the same thing for minus B. It's really minus 1 times B. And then by the distributive property, I can pull out the minus 1. Okay? So that's one thing. And then minus, if you will, minus 1 times something is really the additive inverse of it. That's another thing that's being used here. That'll be homework. Okay. The last part was part C, and it had 2 parts. So part 1, remember, what did it say? Here we're going to let, I think, A be greater than B and C be greater than 0. What do we want to show?
A times C is greater than B times C.
That's right. That's what we want to show. Brad, how am I going to show that A times C is greater than B times C? Well, I'm going to use the definition. That is, I'm going to have to show that A times C minus B times C is positive number. Is that okay, Chuck? Okay, that's what I want to do. I want to show A times C minus B times C is positive. That's the definition of this less than or greater than. Well, since A is greater than B, then by the definition of greater than or less than, however you want to say it, what can I write? Say it again for me, Brad.
A minus B
Is a positive number. Is that okay? By a fact that we've shown, since C is greater than 0, that really means C is positive number. Remember, that was the if and only of fact that I proved that really wasn't in the book. Is that okay with everybody? So here, by the order property, if I take two positive numbers and I multiply them together, what do I get?
Another positive number.
That's right. That means that A minus B times C has got to be positive. Thus, using the distributive property, this would say A times C minus B times C is positive. So what would that say? That says, so AC is going to be greater than BC. And that's what we wanted to show. So that ends part 1. Part 1. Okay. Let's break down the last thing we got to prove. Adam, I'm a little worried about it because I didn't do that one before class. So for part 2, we're going to let A be bigger than B and C be less than 0. We want to show that AC is less than BC. Brad, we got 2 minutes. Melissa, Alabama plays Kentucky, national television, Saturday, 4 o'clock. Don't miss it.
Public service.
Kentucky is the best team in the nation, probably right now. More than likely. But Alabama's got a chance to win. They won't. We're probably going to lose by 62 to 53, something like that. It's going to be a defensive struggle. That's what's going to happen. That's my opinion. You watch the score be 89 to 88, something ridiculous like that. High school. How am I going to show that AC is less than BC? I'm going to show BC minus AC is positive number. Is that okay? That's what I'm going to do. So here's the way I'm going to do it. Since A is greater than B, then A minus B is positive. Since C is less than 0, okay, that means that C is not positive. And because C is less than 0, C isn't 0. So by the order property, that means that minus C is positive.
Greater than 0.
So minus C is greater than 0. Okay, so minus C is positive. Thus, A minus B times minus C is positive. So if I distribute this, it says, I'm skipping a little steps here. It says minus A minus C, and then this is going to be plus BC is positive. I'm skipping some steps here. Some things that you'll have to do in homework to fill in gaps, okay? Facts that are from homework that you'll be using. Thus, that says BC minus AC is a positive number. Okay? And that says that AC is less than BC, and that's what we want to show. So that ends it. And that's all I wanted to do today. So you make sure to look over these again, and next time that we meet is not going to be until Wednesday. Okay, so Wednesday, because we have Monday off. So that'll be the next time. And one of the things, just to give you a little caveat to be excited about, and what you're going to see, the first theorem we're going to prove has 3 parts, the second of which is to show that 1 is bigger than 0. I'm going to say it again. We're going to show that 1 is bigger than 0. You probably, your whole life, essentially, from when you can remember, have known that 1's bigger than 0. But we're going to show it based on what we've done so far. It's kind of exciting. All right, thank you very much for your time and patience.